Yeah.
Okay, so it's our great pleasure to have invited Zach Lipton from CMU. So Professor Zach Lipton is the BP Junior Chair Assistant Professor of Operations Research and Machine Learning at Carnegie Mellon University. He is also a visiting scientist at Amazon AI. He directs the Approximately Correct Machine Intelligence Lab, whose research spans core machine learning methods, applications to clinical medicine, and natural language processing, as well as the impact of automation on social systems. Its current focus includes robustness under distribution shift, decision-making, applications of causal thinking to practical high-dimensional settings that resist stylized causal models, and AI ethics. He is the founder of Approximately Correct blog and a co-author of Dive into Deep Learning book. But without further ado, let's save more time for Zach. All right, let's please welcome Zach.
Cool. Hi, everybody. It's really great to see you all. I wish I could be in San Diego. We could all hang out on the beach, but you know, these are modern times. So I'm going to talk about like one line. Well, it's not really one. I don't know if it's the same line of research, but I'm going to talk about maybe two lines of research today, specifically. One, you know, I guess like here's the like honest answer. I'm going to level with you, which is that I have some new stuff that I'm excited about, but it's too daunting to prepare a 1 hour talk about only the new topic, and I'm insecure about that. So I've got one topic that I feel more confident in. It's older, and I know how to present it, and that's going to be one line of research that I've worked on over the last few years, and then the other is a new result that we just posted in the last week or so, but we've been working on for about a year. So here's like the fake story I'm going to tell for how they're related, or at least the cute story is that one is the label shift problem, and at a high level, at a bird's eye view, the label shift problem is the problem of learning when your label distribution can shift between training and deployment times. And so in this case, you know, learning on the distribution shift, we could say we want to generalize in a more general sense than IID. And distribution shift is a obstacle to be overcome in achieving such generalization. But then I'm going to talk about some new results, which are maybe the converse in some sense, which is a setting in which we're going to actually deliberately introduce distribution shift. We're going to train on data selected from a different distribution than the one that we hope to generalize to, for the very purpose of obtaining like a certificate that we have generalized to the distribution of interest. So, you know, I think it's cute at a narrative structure, although the works are quite, you know, methodologically distinct. I'm pushing it on like my slides per minute because I know I'm a bit long-winded, and I've got almost as many slides as minutes, so I'm gonna like dig into it. Well, my slides are not advancing. Okay, there we go. All right, so Ian already told you a little bit about my lab and our interests, and I guess I'll call out, I guess, the topics we'll be covering today. And I'd like to also call out my student, Saurabh Garg, who really is just, you know, absolutely fantastic researcher who's sort of both of these lines of work are things that we've worked on together, and he's really driving. And you may not already know him, but he's actually here in the Zoom, and I expect you'll know him more and more over the coming years. But I probably throughout the talk will focus on the material, but I just want to make sure at the outset it's clear that Saurabh's been a driving force in this over the last 2 years, and you know, anything that's incorrect or wrong, you should blame me for, and anything that's exciting or cool, you should give Saurabh all the credit for. Okay, so to begin, you know, so this is a line of work, distribution shift, that I've been interested in. It really started at the end of my time at Amazon before, right as I was joining faculty, and I worked on this paper about detecting and correcting for label shift with Yuxiang Wang, who's at UCSB, who's just an absolutely fantastic person to work with. I encourage you all to call him on the phone and get him to come hang out and work on something with him. And with Alex Mola, who was, I guess, both of our bosses at the time and was Yushang's PhD advisor. So I'll mainly focus on the works that are called out in blue. The unified view of label shift estimation was work with Saurabh from a year ago. And then the new work that we're excited about is this leveraging unlabeled data to guarantee generalization. This is my troll of like the glamorous acronym. We've picked a hideous acronym. So to begin, the kind of standard setting for much or most machine learning, or at least the default setting, I think, is this idea that God will shower data out of the sky and we'll harvest some of it, and then we'll fit a model somehow, and we could just assume that God is sort of stateless. So God will the transition function between unlike the God Markov chain is the identity, and so God will shower data out of the sky in the self-same fashion in the future, and as a result, all we need to do to perform well in deployment is to take our data that we got from like the training period and partition it randomly, and we could just, this is as good as deployment data. So this is how we often do machine learning, or how we often, the starting point, the scope of machine learning. And the reality is, who are we to, say what God could do tomorrow? It's got autonomy. And Tuesday is never the same as Monday, and February is never the same as January. And, certainly 2020 was not the same as 2019. But maybe we're making it out of it now. So all kinds of things can go wrong. And, there've been a lot of different angles of this literature, not all of it under the directly positions distribution shift, but that falls broadly under this umbrella. Situations where you are worried about a situation that the thing you're worried about is not that you'll confront IID data and you'll perform badly, but that you'll confront non-IID data and perform badly. And adversarial examples are one such way that could happen. You have some kind of threat model. You say, okay, the underlying distribution will be the same, but could potentially be any sort of push forward through some class of threat models. And we're concerned with the worst case over the threat model. So, arguably the community has focused like overly and narrowly on this like additive L2 bounded noise or L infinity bounded noise. What if you could shift all the pixels one to the right and then apply the noise? Then we're really in trouble. But this is one kind of setting that's consumed people for a while. I have some work with my student Danish, where we show on the adversarial side, this isn't just a problem in computer vision. In text, you can make a single, like a one character edit, such as would, no change to text is imperceptible. Oh, sorry, Herbie is playing with a squeaky toy. I'm gonna close the door. Right, so you can make a single character edit to a document, and you bring down state-of-the-art like BERT model to the level of random guessing on a classification task. And one just like interesting thing to note here as a side note is you might think that a model having access to character level information or subword information like word pieces, which is the preferred tokenization strategy now, would make the model perhaps more resilient because something of the word is preserved even if you've changed the character, versus a word level model where, hey, you change one character, it's just, now it's out of vocabulary. But it turns out these models are more vulnerable. So there's, you could think of it as like a kind of surface area. There's more distinct things you could change the word to, versus to a model at the word level. Most of the changes just basically take a word and turn it into unknown word, unk. But here, each of these different words that you get out of every possible one character attack produces a very different looking word to the model, and you just need one of these perturbations to one of the words to induce a misclassification, and you can conclude that the model's brittle. With two-character attacks, who knows what you can do. So there's all kinds of other problems that arise. A lot of times our training data is not from any task of interest at all. And I think that's actually maybe even one way or another, the maybe like default case, or like the standard here, like ImageNet doesn't correspond to any actual exact task. It's a artificially assembled thing. At least the photographs are real, but there's not like anyone out there who's got a business problem, which is classify these exact 1,000 images that occur in exactly the same proportions. In NLP, the state of affairs is far worse because the data itself is, at least with ImageNet, you could say, all the images are natural photographs, and we're reasonably confident they actually depict the objects that we think they do. In NLP, there's this rush to create benchmarks that often consists of people programmatically creating data sets. So people publish data sets, and then hundreds of people publish methods for those data sets without anyone ever having looked at the data. And there's all kinds of ways that a model can turn out to be very good at these benchmarks and not generalized at all. So one thing that we found here is there's all these models published on a task that's called reading comprehension. It's really just question answering, or answer prediction, maybe even more accurate, a characterization. And people tell stories that we've got this neural attention module, and it looks at the question and it looks at the answer, and it spins them around and turns them upside down. And that's why it's able to perform well. And it turns out that on these very same tasks, if you just replace the question with random words, or you just randomly shuffle the questions that they have no correspondence to the passage, the very same models often get the same accuracy. And so we have no idea what we're doing. But I can tell you one thing, in that it's not question answering. Oh, thank you. I was in the middle of making coffee, but I mistimed it and wasn't able to finish the job. But, love has persevered. Okay, so anyway, all kinds of things go wrong. One of the things that goes wrong is the model itself is sort of self-invalidating. I think this happens all the time. You deploy a model for some purpose, and by virtue of deploying the model, have changed the distribution from which data comes. So I think all these settings that purport to be prediction problems, if you read an ML paper, but are really decision problems. And by virtue of deploying a model, you actually alter the distribution of data. Like when all these user interacting systems, recommender systems, I think are a clear example of this. And you might think, okay, let's make the one classifier that is robust and works all the time, and every setting, and let's just do that. And the problem is this doesn't work. It's just fundamentally not possible. There's all kinds of reasonable conditions that could exist in the world, where one condition would suggest you should do one thing, and another condition would suggest you should do another thing. And so we have to make some kind of, in order to train on data from one distribution and generalize well to another distribution for which we don't have any labeled data, even if we have unlabeled data, we need to make some kind of structural assumption. And I make as like a side note here, if anybody is a note about addiction and gateway drugs. I think distribution shift is maybe the gateway drug to causality, because you start thinking about like, well, what relates the source distribution to the target distribution? And it's like some kind of structural assumption. And you're like, oh, he's making a structural assumption, which, together structure and data, I can identify something, but with data alone, I can't. Then, you find yourself a year later having instant coffee with Buta Pearl and, complaining about deep learning. And that's where we find ourselves today. So here's the paper that got me into this and the thought experiment. I didn't know anything at the time, but fortunately, Yusheng was smarter than me and had pointers to all the right literature to get us oriented. But the problem that was just annoying me was I was thinking about the problem that I guess I now know that there's a literature on it that calls this problem quantification, but I didn't know it at the time. But broadly, the problem is, you train a classifier on some population, and then you're going to use this classifier, and you want to quantify You know, like you train to predict how much cancer there is, how much. Actually, when I made this slide originally, it was I imagined a scenario which was a pneumonia predictor, and then I was giving this talk in London last January, and COVID was outbreaking, and I realized, well, I don't know, it's a bad time. You know, it's maybe you don't want to be, you either don't want to be bringing it up. It's like if you're going to talk about an epidemic, you might as well talk about a real epidemic that exists, better motivated. So I've changed this slide. So imagine that you train a classifier to recognize COVID based on, you know, something like you just have access to all the chest X-ray machines in the country, and you have all the images coming through them, and you also have access to the health records, and you could say, you could learn to predict, you know, is someone diagnosed in the subsequent 2 to 3 weeks with COVID? Try to predict that from the chest X-ray. And let's say you do it, and let's say you do it at a time when, you know, some low fraction of the population has COVID. Let's say it's 0.05%, whatever. You train it on the training data, it does well. You run it on the validation data. You know, say you use some of your validation data to calibrate your classifier and look at the other half, and you say, indeed, it seems to predict roughly 0.05% people have COVID. We're great. We run it in the wild tomorrow. It looks great. And then suddenly an epidemic happens. We run our classifier, and suddenly it's telling us 5% of people have COVID. The question is, how many people really have COVID? And the question that, you know, before we even get to how many people have COVID, we should sort of be like, can we even answer this question at all? Can we say anything? Like, if nothing else, we know the distribution of the push forward distribution through our classifier has shifted, which means that the source distribution, like the distribution over inputs, has shifted, which means IID is violated. So is it game over, or are we done? And, you know, another motivation for this label shift problem is you could motivate it just from thinking about image classification, which is you go out, you train a classifier on like ImageNet, and you know, imagine you train a binary classifier with 2 classes and they're balanced in source data, and you get 70% accuracy and have balanced errors. So it's like, yeah, okay, this classifier is doing good. It's better than the blind classifier. It gets 70% accuracy, not 50%. That's great. On the other hand, if you deploy it in the wild, and now you're getting like, you know, 70% accuracy, but in the wild it's 90% cats and 10% dogs or something, well, you're doing worse than the blind classifier. If only you just knew the base rate, you would be doing better. And so there's this problem that's like, okay, the academic practice is collect these balanced data sets, train on them, and then deploy in the wild and just report whatever probability comes out of the classifier, or estimated probability. But, you know, like, what is this distribution that we're training on? Like, no real life data will contain equal numbers of like axolotls and golden retrievers. There's a lot more axolotls out there. All right, I'm gonna holster my axolotl jokes next time. No more axolotl jokes. All right, and it turns out that, like, you know, we kind of have a high level framing of a process. What we'd like to do is deploy a classifier, detect that there's a shift in distribution, estimate whatever it is that we need to relate our source to target distribution, correct ourselves on the fly, and update our predictions. And indeed, you know, humans have this ability. And so I found this amazing paper from 2010. And of all places, it was the last place I was like emailing like cognitive scientists to ask if there's like any instances of humans doing this, like demonstrably like updating their beliefs without any additional supervision. And of all places, it turns out it was in ICML. So maybe we just used to cast a wider net or something. So there's this cool paper about the test item effect. And what they do is they basically train people on some task that, like, it's not totally natural. It's these artificial weird shapes. What they do is everybody sees the same training set, but some people see test distribution with a certain fraction of just two classes, whatever you want to call them. In giving this talk, I've started calling them weebles and squeebles because I haven't read the paper recently. I don't remember what they're called. Class 1 and class 2. But what they do is, for some people, they show them a balanced data set. For other people, they show them a data set that has way more weebles and squeebles for the test set. So they have no additional labels. But you find that people actually recognize that there's a difference, and they update their beliefs. And they actually, you know, basically you can manipulate people to classify the same item differently statistically by virtue of the other items that appear in the test set. So you could think of it as like when you're in high school and you take a test, and it's a multiple choice test with 4 options, and you get to the end and you realize 50% of the answers were C. And then you go back and you say, okay, for that one that I was totally guessing, I should probably guess C, because I know there's something, you know, I could reject a null that the classes are uniform. So formally, this problem is a domain adaptation problem. We have a source distribution, which is a joint over some inputs x and target y. We have a target distribution, which is some different distribution over x and y. And our goal is and what we have access to is labeled data sampled from the source distribution, but only unlabeled data from the target distribution. So our goal is we want to predict well in the test distribution without seeing any actual, labels sampled from the target distribution. And in general, this problem is underspecified. If I make no further assumptions, I can't say anything about my ability to perform this task. You give me a method that incorporates X somehow, and I'll give you some reasonable assumption under which you're doing the wrong thing. When I say X, I mean the X is sampled from QX. So right, when the distribution shifts, okay, we could just tell if the distribution of classifier outputs is different, that there must be shift. The question is, is that a bidirectional implication or is it only one direction? Certainly if P of X is, certainly if P of F of X is different on source and target, then the distributions have shifted. But isn't necessarily the case that if the distributions have shifted, P of F of X will have shifted in distribution. Spoiler alert is we hope that's the case because it's a lot easier to detect shift in one dimensions than in high dimensional data. Two sample testing in high dimensions is not fun. So we'd like to detect when a shift occurs, estimate the new label distribution, and correct our classifier on the fly. And this picture is just an example of a case where something that we're doing, basically we going through this process, detecting the change, estimating it, correcting the classifier on the fly, results in really good performance when there's a lot of shift versus if you don't do anything, in which case you do not perform well. So high level, here's the applicable assumption that corresponds to my motivating case of a disease whose incidence is changing. We're going to assume that yes, the distribution changes, but there's an invariance. So what changes, we can factorize the target distribution Q as basically Q of X and Y, or Q of Y and X, is equal to Q of Y times P of X given Y. And what this just means is P is the source distribution, Q is the target. All this is saying is, if I change that P to a Q, this is trivially true, it's just a product rule. And so all I'm saying is that it is the class conditional distribution of X given Y that is invariant between source and target periods. That doesn't change, but Q of X can be different from P of X, Q of Y can be different from P of Y, and importantly, Q of Y given X can be different from P of Y given X. And that's important. I think a lot of people, in a lot of the literature, people just say domain adaptation or distribution shift, and they a lot of times will just call that covariate shift. But actually, covariate shift is the opposite assumption. Covariate shift doesn't just say the distribution shifts, it's a statement about what doesn't shift. It says the distribution of covariates could change, but P of Y given X doesn't change. In this case, P of Y given X can change. It's P of X given Y that doesn't change. So it's the converse assumption. And this makes sense. It corresponds, you don't have to tell a causal story to believe this assumption. You could just state it by fiat, but it corresponds nicely to a causal story in which Y causes X. This means that there was an intervention on the marginal of the probability of, the distribution of Y, but the process by which X's are generated given Y doesn't change. So that's sort of similar to you're sort of saying hey, the distribution of the incidence of the disease changes, but what the disease looks like doesn't change. Now, in reality, those problems might be it's still an idealized assumption. This could be a little complicated. Like in the case of COVID, the age distribution of the disease is changing also as lockdown measures change, and the distribution of symptoms is different for different age groups. But you might think, hey, within an age strata, this is a reasonable assumption. And there's a nice paper that I'll just point to here by Bernard Chilkoff called On Causal and Anti-Causal Learning that kind of makes clear a number of these correspondences of how, the Y causes X model corresponds to the label shift assumption, the X causes Y model corresponds to the covariate shift assumption. Yeah. So, you can contrast this with the covariate shift assumption, which is appealing because, hey, we see samples from P of X and Q of X, so we can estimate the relevant, likelihood ratios. The problem is, if we're in like deep learning world where X is some high dimensional object, we don't want to be estimating densities over X. That's bad. We want to be estimating densities over labels. Also note that just if this is the wrong assumption, this will just lead us horribly awry, right? So if you say, what is the probability that someone has COVID given that they cough now versus 2 months ago, the answer is completely different. So if the incidence changes, P of Y given X should change. And if you go back, a year and a half, you say December 2019, in simpler times, if somebody has a fever and a cough, what's the probability they have COVID given that? And the answer is 0. And the answer now is quite a bit higher. So our first stab at this was something that we called Blackbox shift estimation. The high level idea is we want to be able to do something that's effective in deep learning world. We want to be able to work with high dimensional inputs and not worry about the ambient dimension. And so what we came up with is an approach that basically it leverages the fact that we do have good classifiers, at least in the source distribution for most things these days. Just something we could take for granted is that we know how to train a pretty good classifier. I'm going to use good kind of hand wavily now. I'll formalize what notion of good matters soon. And so the idea is we want a consistent estimator that basically exploits off-the-shelf predictor to perform dimensionality reduction. So we're worrying about either one-dimensional data or like k dimensions, where k is like the number of classes in our multi-class problem, not worrying about whatever the ambient dimension is. We're saying as long as we have a good classifier and the classifier isn't too bothered by high dimensional data, then everything else will go through. And what we produce is an adaptive method where if our classifier is good, we get nice error bounds on our estimate of the target label distribution. If our classifier is inaccurate, uncalibrated, biased, whatever, we still have a consistent estimate. It's just, our with the same kind of like rates of convergence, just like our, constant factors might change by quite a bit. So here's the 3 main assumptions here. First is just the label shift assumption. Class conditionals don't change between source and target data. Second, like a basic identifiability assumption that like without it, no method could work, which is just that for every label that we hope to identify and target in the source period, we've seen it with like, had non-zero measure in the source data. Now, there's a slight wrinkle here, which is that under some assumptions, you could, if we have only one new class in the target period, there's actually some things we can do. Like if we've seen k classes and now there's k+1 classes, we have to make some kind of irreducibility assumption, but I'm just not going to go into that now, but that's the topic of current work also with Saurabh. Right, so explanation of the assumption, right? First, that's just our premise. That is the label shift setting. And we need some kind of premise or else just, this isn't a problem that you can analyze. It's just a matter of, throwing things at, various real world settings and hoping that what you come up with aligns with the particular one you're looking at. But 2, identifiability. 3, this third assumption is basically saying we need a classifier whose confusion matrix is invertible. This is the one additional assumption that we require, but I'll argue it's a kind of mild one. Like if the classifier is any good at all, for most problems of interest, the confusion matrix should be invertible. So to see why this works, we can just look at the expected confusion matrices. So let's not worry about estimation. Let's just say, I know the confusion matrix. Like if I had an infinite amount of data from source and target periods, the confusion matrices are different for the source and target data, but they're only different in one key way, which is the scaling of the columns. So Y here is the actual label, Y hat is the predicted label. If you condition on a column, then you're conditioning on Y, and P of X given Y is the same in both the source and target period. And so the P of F of X is also going to be the same. So basically, if we column-wise normalize this matrix, the source matrix, both of them, then they're actually the same matrix. They're only different up to column normalization. And if we column normalize it, we could say now we can estimate, this is now the same object on source and target data. we can estimate it using samples from the source distribution, which are actually labeled. So we could actually estimate all the entries of this confusion matrix. For the data from the target distribution, we don't have the ability to bust them out into the columns of the confusion matrix. However, what we can do is we could just run all the samples through our classifier and just compute what is the mean classifier output on the target data. For now, just think of this as like a normal confusion matrix, like what did you predict? But in reality, like it doesn't have to be. This could be like the softmax outputs of a soft classifier that you're taking the class conditional means and aggregate mean. It's just, you could think of it for now as just like a thresholded prediction. In fact, it could be any function. It just needs to have the right dimension and be invertible. It's just that a classifier is the one you have the reasonable expectation to believe it will actually be invertible. So here right now, what we have is these form a linear system, and the solution to the linear system is the target label distribution. It is the object that we're after in the first place. Now, if you want to like eventually use this in like importance weighting or in reweighting your, if you think you have calibrated predictions, like reweighting and renormalizing them, you'll want to like enforce some kind of non-negativity constraint on your estimates of Q of Y. But basically, C converges to the expected confusion matrix. The mean classifier output on target data converges to its mean at like normal rates. If we have a better classifier, we'll get tighter error bounds, but it's still consistent even if our classifier doesn't have to be calibrated, doesn't have to be inaccurate. It doesn't have to be especially accurate, just enough that the thing is invertible. And so the error bound, and the error bound here is not going to be expressed in terms of the components of the target label distribution, but now here just in terms of the importance weights. This is just Q of Y over P of Y for every label. So our error on recovering the vector of importance weights, which is of length K, where K is the number of labels, is going to be given by this term, which is like 1 over the smallest eigenvalue of the confusion matrix squared, times its terms. It's basically going to have rates that basically, it's consistent in that as you take the number of source data points n used for estimating the confusion matrix and the number of target data points m used for estimating the mean classifier output on target data, as you take both of those to infinity, we converge. And if the smallest eigenvalue of the confusion matrix is larger, then we do much better. And if it's really small, things are really bad. And you can think in the worst case, if the smallest eigenvalue of the confusion matrix is 0, then this is it's undetermined. There's multiple values of target. Like easy case where that might happen is if there's 2 classes where your classifier has no ability at all to distinguish between the 2 of them. It outputs the exact same distribution of outputs for 2. Then there's nothing you can do with your classifier outputs to. So there's no getting around this. So we have some nice empirical results that basically just show. One other thing I would notice here is that what this tells you is also if the confusion matrix is full rank, this also tells you that fixing the classifier, there's a 1-to-1 correspondence between what is the label distribution in the target and what is the mean classifier output in the target. And so this means like if there's been a change in the mean classifier output, there has been a change in the label distribution. And if we've made the label shift assumption, we've committed to the idea that that's the only way in which the distributions can change. So under the label shift assumption, then we can detect shift only by looking to see, was there a shift in distribution of the classifier output? And so we find that, we can, when there's no shift, we have a good estimator compared to say like doing something like MMD on the samples from X. We have good detection under a mild amount of shift. We have really high power under extreme shift. Just sort of confirming indeed that our estimates are consistent as our labels get, as our number of samples gets larger and larger, we do indeed have error approaching 0 for recovering the true importance weights. And the first thing we did was we said, how are we going to use these importance weights? And like one naive way you could use them, or one direct way you could use them, which turns out maybe to be the right thing, is you could say, well, if I thought my predictions were calibrated, I could use these importance weights to reweight and then renormalize my predicted distribution at target time. And the problem there is what comes out of a neural network is sort of in general known to be badly uncalibrated. Forget about for like any true notion of calibrated, even just the if I just look at the like argmax or the predicted distribution, and there's some clumsy heuristics for trying to calibrate neural network predictions, but maybe at first glance not what you want to be doing. So what we did in the first paper, which turns out to be an even worse idea, is we say, well, let's use these weights and do importance weighted risk minimization. So it's a thing that's like a standard, if you're not thinking very hard, which forgive my roots as a humble practitioner, if you're not thinking very hard, it's sort of a standard thing to do. It's like my distributions are different. I know the weights that relate them. I'm just going to resample from my source distribution according to the weights, like do the standard kind of importance sampling approach. The problem here, and indeed it seems to be working. Like we got nice results. Like so what's going on here is as you go from left to right, we're dialing up the amount of distribution shift, and a gap emerges between our basically the approach that's using shift estimation and then reweighting and retraining versus the approach that does nothing, just applies the vanilla classifier. One thing that's unintuitive about this plot, people, they say, why are you doing better as there's more shift? And the reason why is we're starting off with CFAR, so the source distribution is uniform over the classes. Whereas as we have more and more and more shift, we're going towards a world where we actually have all of the mass on one class. So basically, the blind classifier in the source distribution gets 10% accuracy. The blind classifier in the most extreme shift gets 100% accuracy. So in that case, if only we just knew the label marginal, we'd be done. So a few ideas came out from this work, and I'll just put some pointers forward, but I don't have time to go so deep into them. One is, we found that we were doing a really good job compared to maybe some standard approaches for detecting distribution shift when it was there. And so one thing we just kind of wondered is there anything really special about, one is, okay, we've said, okay, you should look at the classifier outputs and then do 2-sample testing on the classifier outputs to detect shift. And this is the right thing to do if the label shift assumption is held. And one question was, is it possible that this is a useful thing to do in general in the wild, even when the label shift assumption is not faithful? And the other question is there anything special about this, or is it really just that we've done, dimensionality reduction plus 2-sample testing, and maybe we would have gotten similarly good numbers if we had done like PCA or trained an autoencoder or whatever. So we had a large-scale empirical study, and surprisingly, using the classifier output seems to be the best representation for detecting all kinds of shifts that aren't actually conforming with the label shift assumption. And that was kind of a weird, surprising empirical finding. So that was one kind of direction we went. Another direction that we went was, we were incorporating the estimated weights by doing importance weighted risk minimization, but there's something about that should jump out as unsatisfying. And the main thing that kept bothering me was these neural networks on these computer vision tasks are trained to basically get perfect accuracy on the training data. And once you get perfect accuracy, it's easy to get arbitrarily low loss because you just increase the norm of your output weights and your loss will approach zero. And it won't just approach zero for one setting of the importance weights, it'll approach zero for any fixed setting of the importance weights. So I saw this talk by Nati Cerebro about work he did with Daniel Sudri. And one thing they did is they were investigating these over-parameterized models. I should be scared now. I have some, superior experts on the topic present. Misha, don't judge me too harshly. But what was sort of weird was, what they find is they say, okay, when the training data is truly separable by the model class, what do you converge to? And they don't know how to analyze nonlinear, realistic neural networks. But they said even for logistic regression, what happens? And the answer they found was this weird result that you optimize on linearly separable with some margin data. You optimize log loss, not a margin loss. You optimize log loss on this data. And what you do is you end up converging very slowly over a long period of time to the max margin separator. And what worried me a little bit was that it basically says you get out the same decision boundary regardless of what weighting you apply. If you're in the over-parameterized world where you could perfectly separate the training data, it doesn't matter how you weight things, you'll get the same solution. And so we wondered, does a similar thing happen in deep learning? So the details are in the paper, and I don't have time to go as deep here as I'd like to, but the weird answer turns out to be, if you take, say, CFAR cats and CFAR dogs, so you have like 5,000 images each and train a classifier, you get about 80% accuracy. So you get to 100% accuracy on trained data, but only 80% accuracy on holdout data. So the weird thing here is, if you set an extreme value of the importance weights, like 100 to 1, essentially, you would hope that this is building in the prior knowledge that, okay, in the target distribution, these aren't balanced. There's 100 times as many dogs as cats. And given the quality of your classifier, you should be able to get to like at least, it's like you should, even if you don't have any knowledge, like your classifier itself is only getting 80% accuracy, and it's roughly balanced errors. So your vanilla classifier just trained on balanced classes should get 80% accuracy on any reweighting of the classes. By upweighting dogs by 100 to 1, you'd think, okay, you should be able to get at least 99% accuracy. But what ends up happening is the classifiers all sort of converge to having almost identical behavior if you train for long enough. So something analogous to like the Sujri cerebral result of like a solution that's actually weight independent seems to happen here. At least qualitatively, in terms of like the fraction of holdout images that are classified as cats versus dogs. So in the end of the day, you train the classifier with no weights, it gets 50, it classifies 50-50 of the holdout images as cats versus dogs and gets 80% accuracy. You tell the classifier, oh, there's going to be 100 times as many dogs as cats at test time, and you incorporate that knowledge via importance weights. If you train for long enough, it doesn't matter. You'll still classify 50-50 and get 80% accuracy. Which brings us back to the topic of and I'm going to even skip on domain adversarial learning. It brings us back to the topic of calibration and vis-a-vis the label shift problem. So here's a quick hit and run on our extensions to this project with Sarab a year ago. So we described this mean matching approach for estimating the target distribution, label distribution, and it gives you a consistent estimator, and everything is nice. However, it's not the only approach out there, and there's another approach that was described maybe 20 years ago that they call EM, but it's not really like EM is the procedure for estimating. You don't even need EM. It's just a max likelihood problem. Is the way they cast it. And basically what they're doing is they're doing maximum likelihood under the assumption that your classifier is actually giving you the true P of Y given X from the source distribution. If this is true, then you could write out a max likelihood problem for identifying the target label distribution that is actually like well specified. And given enough data, the max likelihood parameter should converge to the actual target label distribution. So this approach exists. The problem is you don't have the target, you don't actually have the Bayes optimal classifier from the source distribution. You have some neural network that you trained. In a year after we published our paper, some folks at Stanford pulled out this max likelihood approach, and they applied it, and it performed worse than our approach. So then they said, how do people calibrate neural networks? And they say, well, people use temperature scaling. What if we use temperature scaling? So use temperature scaling, it performs a bit better, but still worse. And then they said, well, the problem with temperature scaling is this just tunes the softmax temperature. It seems to calibrate the argmaxes. If you just look at the predicted classes of each example, and you say, what was the predicted confidence and were you right? You seem to calibrate this number well empirically by some ad hoc measures, but you could still be like badly uncalibrated on each of the predicted classes. Like you could be overconfident when you're predicting dogs and underconfident when you're predicting cats. So they come up with just yet another heuristic, but a slightly more sophisticated one that has, instead of one global tunable parameter, the softmax temperature, they have a per class parameter. So they have k parameters instead of one to tune. And this makes things a little bit more calibrated, if you can tolerate me saying, in a very hand-wavy sense, more calibrated without specifying a good measure of calibration. And this actually gets much lower error than our approach. And what's annoying about this is, like, we know that our approach is consistent and we have a good number of examples. And here's an approach that nothing's known at all about what you're estimating, given that you're using you're just using some off-the-shelf classifier versus the Bayes optimal predictions, and it's performing better than us. Basically, what we set out to do is to figure out, when does this approach actually make sense? And the result that Sarah worked out is, we actually were able to work out the consistency conditions for this method. It turns out calibration isn't just an interesting intuition, it is precisely what is required. What's actually required for this thing to truly be consistent isn't just that things are calibrated in weak sense. They have to satisfy a very strong notion of calibration called canonical calibration. And otherwise, there's no assurance that this thing will actually identify the right parameters. So it seems like to truly be consistent, there's an extremely stringent requirement on the classifier. However, in practice, this bias-corrected temperature scaling with the k parameters does well enough that you actually do get really good estimates. And the other condition turns out to be the very same condition as was required by our confusion matrix approach, which is basically that the confusion matrix of the classifier has to be invertible. So in the work, what we've got here is we sort of decompose the error into two parts, in estimation error and a sort of miscalibration error. So you could think there's a question of, what are we converging to? And is the thing we're converging to the actual true vector of importance weights, or is it something just is it something that's just misspecified and doesn't matter how much data we'll have? And the other side is, how fast are we converging? And so the mystery here is, like, why is this approach beating us? And what Sarab has worked out is basically miscalibration makes this thing misspecified. However, the max likelihood approach doesn't lose so much information because we haven't taken the mean classifier output over each class. We've kept the predictions of our classifier in every single individual example. And so in some sense, like, you're destroying like the Fisher information when you do the confusion matrix approach. And so you converge much more slowly, but you converge to the right thing. Whereas here, you're converging to the wrong thing, but you're converging really fast. Should I say anything else here? Okay, so just one thing that's an interesting note here is that actually the approaches sound like they're very different from each other, but they're actually quite related in that the confusion matrix itself actually is a very blunt instrument for achieving calibration. You can have a calibration where basically you just, whenever the actual label is, cat, you look at, whenever the predicted label would have been cat, you just look at that row of the confusion matrix, and just for all of those examples, you output that row of the confusion matrix. So you'd have a classifier that can only output 6 distinct values. And these are like the distribution of what is the actual class when this is the predicted class. And this kind of calibration actually does satisfy the canonical calibration, but you're throwing out a ton of information. And so it turns out, if you basically calibrate your classifier in this fashion and then do the max likelihood approach, you wind up with estimates that perform exactly this, almost exactly the same. And so it turns out that like what appeared to be a difference between the max likelihood approach and the moment matching approach turns out not to actually be the difference that matters. We could think of it all as doing max likelihood. And in a sense, what really matters, the difference that makes a difference is how are you calibrating your classifier? Okay, we're 50 minutes in. I've got maybe 15 more slides. I hope we could do it. I'm sorry for, I'm very bad at time management. But some of you know me well, so you already know that I'm bad at time management. So far we've talked about our line of work towards understanding a very specific kind of label shift estimation, a very specific kind of distribution shift problem and how we detect it and how we recover from it. Now we're going to kind of shift perspectives towards asking a weird question: when is it actually a good thing to train on a different distribution, or what could be the advantages, even when we're not anticipating a natural distribution shift? Right. So here's a high level view, and I know it's like, what is the deep learning guy doing talking about generalization? So I'm going to paint a picture, and I would love at some point if some of you wanted to chat later and hear perspectives from some folks that have thought so much harder and longer about generalization than I have. I guess I'm lucky that I have some collaborators also who are deeper than I am here, and Saurabh, and also our collaborator as co-advisor, Sivabala Krishnan. So here's kind of like the high level perspective here. We have two ways to guarantee that we generalize. And maybe I'm oversimplifying, so give me just a little bit of license. One is we bound the generalization gap from first principles, something like some property of the hypothesis class, like the VC dimension, the Rademacher complexity, says that we cannot overfit more than a certain amount, and that bounds the generalization gap. In order to actually bound the generalization error, we still have to train on the training data, because we have to obtain the empirical risk to plug it into the bound, to bound the population error. So that's one thing we could do. We could say in the first place, what's our capacity to overfit, and then we can train a hypothesis in that class and plug it in, bound the generalization error. And the other approach that we have is we say, let's just train our model, principle be damned, but we're going to afterwards, we're gonna partition, we're gonna hold out some data, we're gonna evaluate the model. So this isn't a guarantee that we will generalize, but it's a certificate that we have generalized when we achieve a certain performance on the holdout test set. Now, I want to be clear in the first place that we're not making either of these obsolete or purporting to replace the sort of normal like learning theoretic analysis, or to suggest that people should stop using the validation set, but rather maybe I should temper this to be like what we hope is an interesting result that maybe gives a new perspective and an interesting direction for thinking about generalization, or shifts the burden somewhere else. So one thing that's maybe unsatisfying about the a priori bounds is that we don't know how to make them for the models that we care about today in the modern high dimensional data deep learning world. We don't know how to establish a uniform convergence type bound that actually assures generalization. And on the other hand, the train test split is also a little bit unsatisfying in that successive reuse of the same holdout set in principle can lead to adaptive overfitting, although there's some interesting results on how it's surprisingly absent in some of these large scale benchmarks. And it restricts the amount of data available for training. And I would add to this, one thing is sometimes we find out that we never had a test set in the first place. So someone discovers there was a bug in their data processing pipeline, and you actually don't have any test data because your test data overlapped with your training data, and you've already trained a bunch of models. And so at this point, you might find that just the whole proposition of having a test set is out the window. And so the window here, the idea here is, can we leverage unlabeled data to obtain a generalization guarantee? So we're not going to guarantee that you will generalize. What we want to guarantee is that you have generalized. And the key idea is we're going to create distribution shift. So we're going to alter the training distribution. So we're gonna take some unlabeled data, and we're gonna assign random labels to the unlabeled data, and then we're gonna toss it in the cauldron with the clean labeled data. We know which data is which. The ML algorithm does not know which data is which. We're gonna train the model, do our sort of standard, risk minimization. And at the end of the day, what we want to do is we want to establish generalization by showing that basically if we have fit to the clean data, but somehow, despite training on the mislabeled data, have not fit it any better than random, then we have in fact generalized. And so the interesting thing here, or way that we're sort of shifting the burden, is we're not guaranteeing that this will happen in the first place. We're saying even if you couldn't guarantee that this would happen, if this has happened, then you have generalized. So maybe you don't know how to characterize the relevant notion of complexity of the hypothesis class, but still this condition has happened. Then we want to be able to say that we have, after all, generalized. Again, just caveats, we're not saying this is a replacement for the holdout approach. I think that would be crazy. I also don't think it's a replacement for understanding basic learning theoretic concepts. I think that would be crazy, but just something interesting. And the important note here again is that our post hoc bounds do not depend directly on the complexity of the underlying model class. So again, pictorially, we've got the labeled data. We grab some of our unlabeled data that's sitting out there. So you imagine you had 1 million examples, but you could afford to label 100,000 of them. So you've got those. You grab some of the unlabeled data that you don't have labels for. You assign random labels, toss it in the pot, train on it, and then you're going to track your performance. So some notation. We have some clean data S. We have some randomly labeled data S tilde. We have the distribution of clean data mathcal_d. And the thing that we care about bounding is the error of the classifier on the true distribution. So here's the main result. The main result is that, and now for simplicity, we're just saying, say you have balanced classes, and just doing binary classification, that basically your population error is bounded by the sum of your error on the clean sample plus 1 minus 2 times your error on the randomly labeled data, plus some term that decays with 1 over root m, which is like the size of the mislabeled data. And the high level idea of the proof is that basically the way that we're going to prove that generalization has happened is we prove that overfitting happens. So what we're going to say is your data consists of it's a mixture of 2 components, the clean data and the mislabeled data. And the mislabeled data itself is we don't know which of the mislabeled data is clean. The randomly labeled data is actually correctly labeled versus mislabeled, but it's a random subset. So what we're going to say is we're going to first just look at the mislabeled data versus the clean data. So we're able to back out our error on the mislabeled data because we know our error on the clean data, and we know our error on the randomly labeled data, and we know that the randomly labeled data is a mixture of clean and mislabeled data, and we know what the mixture coefficient is because that's given by the base rate. So basically what we're going to do is we back out to the error on the mislabeled data, and then the key is to say your error on the mislabeled data that you tried to train on is going to be lower than the population error on mislabeled data. So what that means is basically like you're gonna have lower error on mislabeled data that was included in training than on mislabeled data sampled freshly from the population. So it's like training on things gives you lower error than the population, that's sort of intuitive. And then if that's the case, well, the error on the population is actually equal to sort of the accuracy on the clean population, because of the complementarity of mislabeled, of error on basically what makes it mislabeled is there's a label flipping operation. So if you've got an error of 0.99 on the mislabeled data, it means that you have an accuracy of 0.99 on the clean population. So we have this result for ERM on 0-1 loss. We can say that in general, the bound given by this will never be larger than the Rademacher complexity bound. We can extend it to the more realistic setting, which is you're not always going to be doing ERM on 0-1 loss, but more likely optimizing some convex surrogate. So we have results that extend to linear classifiers trained by gradient descent on squared loss, and show that still a bound of this form holds in terms of the 0-1 error, despite the fact that you're training on squared loss. The bound extends to kernel regression, it extends to wide networks in the NTK regime, and it extends to early stopped gradient descent. In the case of deep learning, we have to make an additional assumption, but in practice, it seems that we're unable to find instances where the assumption is violated, and the bound seems to actually be quite predictive, at least in the first, tens of epochs of the test error. And what this sort of relies on, or what we take advantage and inspiration from, is this what's called the early learning phenomenon. The fact that is well-documented empirical result that when you train on noisy labels, it seems that the models fit the clean data before they hit the noisy data. Even in these papers like the understanding deep learning requires rethinking generalization, yes, they're able to fit the random labels, but if you look at the curves, it takes them much longer to fit the random labels. And so this seems, we can't guarantee a priori that this will happen, but we know this is a thing that happens. And when it does happen, we're able to take advantage of it to produce a certificate that we have in fact generalized. So that's about where we are. Here are some empirical examples where we're training models and we're not looking at the test set, but what you're seeing here is the predicted bound in the dotted lines that comes just from looking at the error on the clean and randomly labeled data. And what you see in the solid blue lines is the actual test set performance that we're not looking at. So it seems to track it quite closely for quite a long time. So I think this is a good place to stop. Sorry to run a few minutes over, and I'm happy to hang out and answer any questions if anybody's left and not sick of me at this point. So anyway, thank you.
Great, thanks for speaking. If anyone has any questions, I guess go ahead and feel free to chime in or write in the chat.
There is one question in the chat from Mario. Does it sound like the conditions are more likely to be satisfied by low complexity models? So low complexity models, perhaps, I mean, here's where we're shifting the burden. I feel like with low complexity models, you have a better hope, or you have direct means by which we can prove that these conditions will be satisfied in the first place. However, the thing that's maybe interesting here is that with high complexity models, for which we don't know how to prove this will happen in the first place, it seems to happen anyway. And so what's interesting about the result maybe is that just like, okay, first principles tell you it should happen for low complexity models. We don't know why it should or shouldn't happen for, say, deep learning models, but it happens anyway, despite the fact that we don't know why. And so the fact that we're observing it happening means that we're able to, it's like, that's why I say like we're sort of like shifting the burden. We're not certifying that it will happen. We're saying that this is a well-documented empirical phenomenon. We're able to, basically, we're able to certify that we have generalized when it does happen. And we're pushing it now onto the we're pushing, like, early learning is known to happen. When it happens, we give you a guarantee. and this pushes now guaranteeing generalization to guaranteeing early learning. So I hope that maybe gives like a little bit of insight there. Of course. Anyone else have questions?
Yeah, if I may insist, I'm asking because at the end you said that when you have this deep learning models and you train them just a few times or something, it sounds like replicating low complexity to some extent, right? I mean,
it
sounds like you're replicating low complexity. You know, to some extent, even though you have a high complexity model, you are just using like a low complexity part. And I'm asking if you have a proof, I mean, like theorem that if you have low complexity, BC dimension less than something, then you have those conditions. Because I mean, that's a good start, right? I mean, you have the low complexity model should satisfy those conditions.
So you
are training a few times.
You have that, how do you put it? Yeah. So I think you already have it in the first place. Like you don't have to add randomly labeled data to have it, right? Because that's sort of like what a VC bound is telling you in the first place. It's saying you don't even need to add the randomly labeled data. You can just train on this much clean data and certify that you haven't fit to that you generalize, right?
I see. Now I understand.
So I think that's straightforward. You might be able to prove something better specifically. You might be able to say something about specifically this setting, but it's like in the first place, maybe that's in some sense maybe not the case you're worried about. I think the weird thing is that, okay, the deep learning model in general can overfit arbitrarily, right? Like we sort of know this, at least on the sizes of data sets of interest. It can get zero, it can get zero error on the randomly labeled data. And if it gets zero error on the randomly labeled data, the bound becomes vacuous and it guarantees nothing. So we know that there exists a set of parameters that achieves this. And so then the question is, like the hypothesis class, as defined as like all neural networks with this architecture, all settings, the possible settings of the parameters, you can't in general guarantee generalization by looking at the training data for that. And so the tricky thing then is like, well, what about, you know, early stopped gradient descent? Can you guarantee something for that? And the weird thing then is like, what is the relevant notion of the hypothesis class? It's not clear. It's not clear how the complexity of that hypothesis class is defined. And so what we're sort of doing here is saying, well, you may not even have to define it. So that's where things get kind of weird. It's like you have these like ill-defined hypothesis classes, which is like what you find after X number of steps of gradient descent on this big model that, given arbitrary time, can overfit arbitrarily. And looking at the training data would tell you nothing about generalization, but you know, what can you say about this model, you know, like that is like trained by SGD for, you know, n epochs, whatever. And the answer is a priori we don't know, but you know, post hoc we can actually say something.
Yeah, I see. Thank you. So you're bypassing completely the necessity of defining a new notion of dynamical complexity or anything like that. I see. Thank you. Yeah.
Yeah. So that's the weirdness. And it's like, I think the charm here is that we're sort of saying, like the fact that like we don't depend directly on the complexity. It's like there's an indirect thing going on. Like there's an implicit, there's something like an implicit notion of an empirical Rademacher complexity, but it's like for a hypothesis class, it's defined in a strange way where like we don't actually know what is the, you know, Rademacher complexity of early, 40 epoch trained ResNet, 400, whatever. So there's something like it, but we're pushing it into the, instead of pushing it into the, having it in the certificate, we're pushing it into whether or not the conditions would have arisen by which we can make the certificate. So we're able to make the certificate without knowing the complexity, but we wouldn't have been able to make the certificate if there wasn't something about either the hypothesis, class, or search procedure that made those conditions arise. So it's sort of saying like we're able to certify generalization based on this, but not knowing why this happened, if that makes sense. Cool. Any other questions? All right. Well, I think I might have a chat with Rajesh. And Saurabh is here. Saurabh, you could turn your, for the 4 remaining people, you could turn your camera on and say hello. All right. Maybe not. Anyway, take care, everyone. It was nice to meet you.
Yeah, thanks so much for speaking.
Oh, no problem.
Take care.